Hello, welcome back. This is Calculus by Dr. Oz. Today we have an exercise where we're going to have numerical, graphical, and analytic analysis for a given geometric series, 10 minus 1/4 to the n minus 1. We have three things to do. First, we're going to find the sum. Then we're going to list the partial sums for certain n values, and partial sums are represented by Sn, by the way. So when we say, for example, S5, we're going to take the sum of the first 5 terms. If it's S10, it's the sum of the first n terms. I'll explain that in a sec. And in part C, we're going to use the graphing utility to graph the data in the table. And eventually, we're going to sort of like assess if the partial sum converges fast or slow. So based on the magnitudes of the terms of Sn, which is the partial sum. All right, so this is sort of like a relatively longer question. All right, let's start. Let's hit the road.
All right, let's start. Let's first find the sum of the series by using the geometric series formula. So let me just recall this formula. And remember that if you have a geometric series of the form a times r to the n, and n starts from 0 going all the way to infinity, depending on what r is, then you can say like the series is convergent divergent, and for convergency you need the absolute value of r to be less than 1, which is essentially minus 1 r and 1. So if you have r in between -1 and 1, then you can just write the sum in one shot. So going back to the given series here, I can perfectly conclude that a equals 10 and r equals -1/4. This implies that the absolute value of r is 1/4. So that is less than 1. So this geometric series converges. Okay. And what does it converge to? So n from 1 to infinity minus 1/4 to the n minus 1. Maybe I should make a little comment here. So here the sum starts from 0, but this one starts from 1. So does that matter for this type of problem? Well, it doesn't matter, because then the exponent here is n minus 1. So what we want here is that the very first term in the sum to be 1. So when n equals 1, this exponent becomes 0, so that's -1/4 to the power of 0, which is 1. Okay, so we want to make sure that the very first term in the sum, forget about this term obviously, I'm talking about the exponential term. So the very first term, starting from the lower limit of the sum, you should have 1, and which is the case. Okay, so you don't have exact same form of this as long as you have the sum starting from some number, but the very first term in the sum is going to be 1. Okay, so this sum has to be equal to a, which is 10, over 1 minus r. R is -1/4, so let's write that down. Okay, so that implies 10 over 1 plus 1/4. Okay, so let me just clean this part to continue. So that's equal to, so this is 5 quarters. So if you flip that over, it's 10 times 4/5. Okay, that's 40 divided by 5, and that is equal to 8. All right, so based on the use of this formula, I can go back and say like this sum is in fact equal to 8. All right, now I can go ahead and come back here and conclude that this sum is equal to 8. So in the next stage, we're going to use a graphing utility to find the indicated partial sum, Sn, and complete the table for different values of n. Okay, so for example, so if this is a n, Okay. S5, for example, is going to be A1 plus A2, all the way to A5. So at this moment, why don't you have your calculator ready and try to find the partial sums for different values of n. And I made a little mathematical code just for presentation purpose, just to see what the partial sums look like for different values of, here I use the capital N notation, but it's essentially the same. So for n equals 5, 10, let's see, 20, 50, and 100. I think I started from 1 and I went all the way to 100. You can also pause the video and then see the corresponding values. I kept only 3 decimal places for the partial sums, but after certain numbers of n, as you see that the sum is 8. So here the convergence is not bad. So starting from, let's see, keeping only 3 decimal places, maybe starting from here and here, like after n equals 5, you are in the neighborhood of 8. So if you follow those dots, see, like, this is a very fast convergence. Okay, it's a very rapid convergence, and in fact that also explains part D, because it says like explain the relationship between the magnitude of the terms of the series and the rate at which the sequence of partial sums approaches the sum of the series. Well, I can perfectly feel here that this sum converges to the partial sum converges to 8 very, very rapidly. All right, so this ends the video. Thanks for watching. I'll see you in another video. Bye.